Here in this graph, we have a standard normal distribution curve. Okay, so it has a few key features. You'll notice the middle of it is now at 0, and it goes from negative values up to positive values. So in statistics, you often talk about how far below the mean or above the mean you are. And usually you talk about those in terms of numbers of standard deviations above or below. So this standard curve has an average right at 0, and then a standard deviation that is 1. So you're making all measurements in terms of the standard deviation. Okay, so you talk about how many standard deviations above or below the mean you are. And so this standard curve describes that well. Now, a thing that we're very interested in is the proportion of a population. So this would represent some set of data, all right? Some data sets fit bell curves very well. Some do not, right? So when you're looking at a data set, it might not be from flipping a coin. It's probably, you're measuring heights of kindergarten students or something like that, or weights of acorns, or things like that. And they tend to have a central value that they cluster around, some average, and then you have most of them sort of clustering around that middle value, but there are some that are more extreme on the ends, but not many of them. All right. So the first thing you want to do when you have a data set is determine whether it should be represented as a normal curve or not. So a good way to do that is to literally take the data and make a histogram out of it. And if it looks like a bell curve, then you can describe it pretty well with the normal distribution. So what I want to show here, though, is the probabilities of being in certain ranges, certain numbers of standard deviations away from the mean. So if I start with A equals 0 and I set B equal to 1, we'll get a probability calculation out of this. Right? You can see we shaded in a region from 0 to 1, and that would be 1 standard deviation above the mean, which was at 0. And you can see in the title, there's a 34.1% chance, or 0.341 proportion, that the data will fall between the mean and 1 standard deviation above the mean. If we were to look at the area from 1 standard deviation up to 2 standard deviations, and shade that in, we'll see it's only about 13.6% of the data. And if we fill in from 2 to 3 standard deviations, it's a very small percentage of the data. It's sort of like tossing a coin. We don't expect to deviate by a lot from the mean. It's unlikely that we would, all right? So let's go back and let's put in some negative numbers here. What if we were to go from -1 standard deviation up to 1 standard deviation? This will correspond to what the book shows in one of the blue boxes. It said about 68% of the data falls between -1 standard deviation below the mean and 1 standard deviation above the mean. If you look at the title of this graph, you can see that's 68.3%, and even that is an approximation. So it's fair to say about 68%, which is just over 2/3 of the data, if you have normally distributed data, will fall within 1 standard deviation of the mean, from 1 below to 1 above. This means if I randomly take a piece of, or one member of the data set, there's about a 2/3 probability that it would fall within 1 standard deviation of the mean, right? Also helpful when you're looking at the statistics of numbers, if you go out to 2 standard deviations in either direction, if the data is normally distributed, we can see it's going to be a larger percentage of the data. So we go from about 68% up to about 95%, right? 95.4 is a little more precise, but it's an irrational amount, but it's approximately 95%. So if you want to be 95% certain that your data, that an element of a data set at random will fall within will be near the mean, you want to consider plus or minus 2 standard deviations from the mean. It's likely then you would be 95% likely that the element you pick would be within that range. If you go plus or minus 2 standard deviations. If we go out to plus or minus 3 standard deviations, we essentially include all of the data. If I shade that in, I can see that proportionally I've shaded in nearly all of the area. That's 99.7%. So that's saying it's very rare for data to fall to be over 3 standard deviations away from the mean, either below or above it. In fact, if we were only looking at what's the probability of being more than 3 above, we could go from 3, actually we'll just go 3 to 4 because there's very, very little data beyond that. You can't even see the shading, and you can see that it's about 0.1% of the data would fall from 3 to 4 standard deviations, and it'd be significantly less from 4 to 5. So most of the data is clustered around the mean when you have normally distributed data. We could see that when we were doing something like tossing a coin, the data is approximately normally distributed. So many things that are truly random will be normally distributed. But other data sets, like if you were just looking at the number you would roll on a die, you're just as likely to get 1, 2, 3, 4, 5, or 6. That is not normally distributed. So the would not be good to use a bell curve to describe that data, all right? So let's look at a problem where we could use this curve. Let's look at the problem of the average height of a man. All right, so I'm just going to make up some numbers. I didn't actually look up any of this data, but let me assume that the average height of a man is 70 inches, right? That's 5 feet 10 inches. Let's assume that men tend to fluctuate by about 2.5 inches, all right? So remember, if we go out a standard deviation in each direction, so that would be from about 67.5 up to 72.5. We would expect about 2/3 of the population to fall in that range. And that's probably about right. Let's figure out, though, the probability of someone being over 6 feet tall, okay? So if you want to look at the probability of being at least 6 feet tall, let's say, that's 72 inches, 12 inches in a foot. So 6 times 12 is 72. And we want to have anything larger than that. Well, realistically, people aren't over 8 feet tall, let's say. So let me just put in, if you were to take 8 times 12, you would have 96. So I'll just put 96 in because I don't think anyone is over 8 feet. Okay, every once in a while you get somebody who's a little bit over 7 feet, but not over 8 feet. So let's see what happens when we graph this. Okay, so you can see we essentially shaded all of the area above 72 inches. And if you look at the title, you see the probability from x equals 72 to x equal 80 is 0.212. All right, so that means there's about a 21.2% chance of someone being over 6 feet tall if my average and standard deviation are correct. And that seems about right. Probably about 1 in 5 men is over 6 feet tall. So that seems to work. Okay. Now, another thing you should note in this data of heights of men, unlike flipping coins where we have to have a certain number of heads, the height of men is continuous. So this bell curve may actually be a better way to approximate heights of men rather than when we're flipping coins, we're really using the bell curve to approximate a histogram. So the heights of people do not fit into bins quite as neatly. We can make bins to put the heights in, but the heights could fall anywhere within a bin. So it's a little bit harder to define lines. So it's a little bit more of a continuous function that could be mapped nicely by this bell curve. So we can figure out the probability of this happening. We could also have calculated that using our calculators on the TI-84. Let me just remind you of how to do that by switching over to my iPad. Okay, so you can see I have the instructions from before. We'll follow the same instructions. Go ahead and get your calculator and make sure you know how to work this out. So we can put in second Bayes distribution is what you're actually picking, the second function over variables. You want to choose the normal CDF. This time, after you choose normal CDF, we want our lower limit. Remember, that was the 72 inches. That's the 6 foot mark. The upper limit, technically it's infinity, but we can't go to infinity. So we can just pick an absurdly high height. Maybe you could even put in 100 inches, which would be absurdly tall. So there's some probability of vanishingly small. Somebody would end up there. Probably no human has ever actually been up there. Well, I guess maybe some of the giants. Goliath was up there. We have a mu value of 70 and a sigma value of 2.5. All right. So those are the things that would go in for this particular case. And then you will choose to paste it. And when you select paste and hit enter, paste will get you back to your working window. And when you hit enter, it should give you the value that we attained just a few minutes ago. And you should see that it's about 21% of the population of men would be over 6 feet tall. Okay, what would that correspond to graphically? It's just what we saw. We're up here finding the area to the right of the 72-inch line when the mean is right there at 70 inches. Okay, so let me pause for just a moment. Okay, so I'm collecting my thoughts. You all are lucky. You are in the day of having a calculator that can simply do that calculation. Okay, just like you saw visually in MATLAB. All right. Back in the old days, what we would have done is taken this problem and we would compare it to the standard distribution, which I showed you a little bit ago, that was centered on an average value of 0 and a standard deviation of 1. And you would have books full of probabilities. You might have, what is the probability of going from x equals 0 out to 0.1. And then in another line of the table would be 0 to 0.2. And those numbers would go all the way up to 0 all the way up to maybe 4 standard deviations out. So you can see if you went by tenths, this would take a long time. If you went by hundreds, you'd need an even bigger book to contain all of the values. But you could figure out the probabilities for shaded regions that people had worked out, and you would look it up in a book. But you needed to compare it to the standard curve. So what we would have done with the numbers is we would have said 72 inches is 72 minus 70 above the mean. So it's 2 inches above the mean. But what we would really need to know is how many standard deviations above the mean that is. So we would give that number a z-score, and the z-score would be 2 over the standard deviation, which would be 2.5. So roughly, if I double those, 4 out of 5, or about 0.8. So 72 inches would have a z-score of 0.8 because it was 0.8 standard deviations above the mean. Okay, so we could say 72 inches is 0.80 standard deviations above the mean. So when you look at the standard normal distribution, everything is measured in units of standard deviations above or below the mean, and the probabilities can be found. So if you wanted to, you could have figured out the same question by making lower equal to 0.80. You could make upper. You can make it anything you want. That's a big number. If you go out to 4 standard deviations, that would be enough. You could go, if you wanted to, though, you could go you can go as high as 10 standard deviations. It will just take longer for the calculator to calculate it, and the answer really won't change by much. And then you would put in a mu of 0 because it's 0.8 standard deviations above the mean. So we're measuring it relative to the mean. So we put the mean back at 0, and sigma would be 1. So if you put all of those numbers in and paste, enter, you should get the same answers. So we've just translated the problem into a currency of how many standard deviations above the mean we are, rather than putting the value of the mean and the range of values we're looking at and the standard deviation into the calculation. So you could do it either way. The second way is sort of the old-fashioned way, because the only curve for which you had the area was the standard normal distribution, but now calculators can handle non-standard normal distributions quite easily, so it's just easier not to have to make the conversions.